Hello everyone, welcome to section 3.1, beginning of chapter 3, where we're going to start talking about graphing polynomials. So the very first type of polynomial that we're going to graph is something called a quadratic. So let's go ahead and write that down. What's a quadratic? So I guess definition. A quadratic is a second degree polynomial. It's a second degree polynomial and it has the following form. So we'll call it f of x, which is equal to ax squared plus bx plus c. In this case, we need to make sure that a is non-zero. Okay, so what does the word polynomial mean? Polynomial, poly means many, nomial you can think of terms, polynomial means many terms. Here you can say I have 3 terms. What a term are things separated by additions. We have 1, 2, 3 terms. It's called a second degree polynomial because the largest power on the variable x is a 2, so it's a second degree. The reason we need a to be non-zero is because if a was 0, I wouldn't have that x squared term. I just have something that has a bx plus c. This would actually be something that would be an equation of a line. So we need to make sure that a is non-zero. Okay. So our goal in this section is we want to graph polynomials. We want to graph quadratics. So that's our job here. So let's go ahead and begin with the simplest quadratic I can possibly think of. The simplest quadratic would be something of the form x squared. So let's go ahead and graph this x squared. What does that look like? This looks like the timeless, the classic, the parabola. Okay, it has this general shape because just think about inputs and outputs here. So let me write this. This is x squared and this is x. When I plug in 0, 0 squared is 0. When I plug in 1, 1 squared is 1. When I plug in 2, 2 squared is 4. When I plug in 3, 3 squared is 9. So it's growing pretty quickly. That's why it's kind of curving upward. And over here, when I plug in negative values, plugging in a negative value and squaring it gives you a positive value. If I plug in -1, -1 squared is 1. If I plug in -2, -2 squared is 4. If I plug in -3, -3 squared is 9. So that's why, actually, if you kind of think about the outputs I did over here and the outputs over here, parabolas are always symmetric. They're always symmetric. And a good thing to notice about a quadratic is this piece I have at the origin. This would be the minimum value of this function. We call this the vertex. The vertex of the parabola. For the simple quadratic x squared, its vertex is at the origin. It's at 0, 0. And all quadratics will always be symmetric about the vertex. So this is the simplest quadratic I could possibly sketch you. Okay, let's look at a different example. Let's look at a different example. So what I'd actually like to claim here, and we'll show you here in a second, a claim. Any quadratic, so anything that's in this form, any quadratic is a transformation of x squared. That parabola I first drew you, any quadratic, anything that looks like this will simply just be some sort of transformation of x squared. This might be a good time if you're uncomfortable with function transformations or you need a quick review. Please go take a look at the video I did for a review of function transformations. So this is what I'm going to claim here, and I hope to convince you of this by the end of this lecture. Okay, so let's do an example. So in the very beginning of this lecture, I just want to draw simple, kind of loose sketches of quadratics, and then we'll get more detailed as we go. So let's do another example. Okay, so let's say that I want to sketch the graph, a loose sketch of the graph, let's say f of x, which is equal to x minus 2 squared plus 5. And in the back of our head, the back of our mind, let's keep this graph, the simplest of the quadratics, in our mind. So when I look at this function here, this new one I've drawn up here, I hope we can clearly see that this is just a transformation of x squared. How have I transformed this function? Well, notice what I've done here is I've subtracted 2 directly from the x value. So what does that do to my graph? It's going to shift it to the right 2 units. So when I subtract 2 directly from the x, this shifts x squared to the right by 2 units. And what is this plus 5 doing? Well, what I'm doing is I'm adding 5 to the outside of my function. I'm increasing my input, my outputs by 5. This is going to shift my graph up. This is going to shift x squared up by 5 units. So if we're just thinking about function transformations, I can very easily sketch this graph. Let's do it. So what have I done? I've taken this graph, I've shifted it to the right 2 units and up 2 units. What I've done here is I've shifted a great kind of point to hold on to is I can think that I've really shifted the vertex. It used to be at 0, 0, but I've moved it to the right 2 units and up 5 units. So the vertex of this parabola will be to the right 2 and up 5. So here I have a beautiful sketch, a beautiful loose sketch of this function here. And all I needed, I didn't have to plot points. I didn't have to make any t-table. I just remembered the graph x squared, what it looked like. I thought about function transformations. I can get a loose sketch. So what's beautiful here is, I guess let's write down where's the vertex now. This is the vertex. The vertex is now at 2, 5. I've shifted it over 2 units and up 5 units. I love this form! I love this form! Let's do another example. Let's do an example that's not as friendly. So, let's try to think about a sketch of the function f of x, which is equal to x squared plus 4x minus 1. Oh no! I don't like this form! I can't see how it's a transformation of x squared! How has this been moved? How has it been shifted? I can't see it. Where's their vertex? This is a problem. So what do we do in these types of situations? What we want to do, a very common thing we do in math, is we try to massage functions. We try to massage equations to get them into a form that helps us see what's happening. So this is what I want to do here. What I would like to do is I would like to try to massage this function so I could see it as a transformation of x squared. A general form, I would like to maybe take x minus, let's say, h plus k, and then maybe put an a out front. If I could massage this function to look like in this form, it would be telling me all its secrets. In the case where h is positive, this would be telling me that I'd be shifting x squared to the right by h units. If this k here is positive, this would be telling me I'm shifting x squared up by k units. Or in this case, maybe where h is negative, I'd be shifting it to the left by h units. If k was negative, I'd be shifting it down k units. And what would this a tell us? Well, if a is positive, remember when we multiply the outside of the function by a number, let's say 2 for example, I'm going to take all my outputs and I'm going to scale them by 2. That's going to stretch my graph. If a is maybe a fraction, maybe like 1/2, it's going to take my outputs and it's going to compress them by a half. Let's draw a quick sketch of what this form here is telling us. There's two situations. Let's assume that a is positive for our first example. That means I'm multiplying the outside of a function by a positive value. That's either going to stretch my graph or compress x squared. I'm going to be shifting it to the right h units and up k units, assuming h and k are positive for now. So what's that going to look like? I'd be shifting it to the right h units. And maybe up k units. Again, for right now, I'm just assuming h and k are positive. This is where the vertex of the parabola would be. And now all I'd be doing is I'd be shifting it, but I would be either stretching or compressing it. So the graph, since a is positive, I'm going to have a shifted happy face parabola. A is positive, I get a happy face parabola. Now if a is negative, what's going to happen? So I would still be shifting it, again, assuming h and k are positive for now, I'd be shifting it to the right h units and up k units. But now if I'm multiplying the outside by a negative value, I'm multiplying the outside by a negative. So if my outputs were positive, I'm now making them negative. That's going to reflect the graph over the x-axis. So if a is negative, I'm going to have a frowny face parabola. So the graph will look something like this. And its vertex will be at h and k. This form has a name. We call this form of a parabola, I call it, most textbooks call it, the vertex form. Why is it called the vertex form? Because if I can write a quadratic in this form, it's screaming at me. It's screaming at me where the vertex is. It's at H. It's at HK. It's at HK. But the book, unfortunately, calls this something different. I'll write it in red because I hate it. The book calls this standard form. You know what I think about that language? I think about it like this. Why would you call it standard form? Every textbook I've ever seen calls it vertex form. An appropriate name because it's screaming at me where the vertex is. What I have always been taught what standard form is of a quadratic is ax squared plus bx plus c. So you might hear me in these lectures talk about vertex form, but when I say vertex form, I'm referring to what the book calls standard form. So just be aware of that. Okay. So this is vertex form, and that's what we want to do. We want to take any sort of quadratic and we want to massage it into vertex form so I can clearly see where the vertex is. Let's do a couple examples. So how are we going to do this? How are we going to do this? Okay. Let's write up our key thing we want to do. We want to massage these functions into vertex form. I want to make a quadratic look like a x minus h squared plus k and some sort of a out front. Okay. So how are we going to do this? How are we going to do this? Keep this little note right here. How are we going to do this? Well, the thing to notice about this form specifically is this x minus h squared piece. This is what we call a perfect square. So what I'm going to want to do here is I'm going to want to complete the square on this quadratic. This is the perfect time, if you are uncomfortable with completing the square, to go ahead and take a look at my video for the review of completing the square. So recall, whenever we want to complete the square, we want to complete the square, let's write it in a different color. We complete the square on something that's always of the form x squared plus bx. So whenever I complete the square, I always want the coefficient in front of the x squared to be a 1. So if I have something of the form x squared plus bx, that's what I want to complete the square on. Over here, I have that x squared plus 4x, so in this case, the b in this situation would be 4. So I want to complete the square on this x squared plus 4x piece. So let me show you how to do that. So what we're going to do is we're going to group together the very first two terms. We'll go ahead and group together the x squared plus 4x. I'll leave myself a little bit of room here, and I have that minus 1. So all I've done here is group these two terms together, left myself a little bit of room for some work. So how do I complete the square? Recall what I do is I take the coefficient in front of x, in this case it's a 4, I cut it in half and square it. I'm going to take this 4, I'm going to take this 4, I'm going to cut it in half, and I'm going to square it, so I'll have a 2 squared. So what I want to do is I want to add 2 squared inside these parentheses so that this will factor to a perfect square. Okay, I'm going to do it in blue. So we'll add a 2 squared. Now you could go ahead and write this as a 4 if you'd like. I usually like it writing it as 2 squared because it reminds me how this will factor. But be careful! Be careful! I've added 2 squared to the function. I can't just go adding 2 squared. If I just add 2 squared, I change the function. So what I'm going to do is I'm going to use the second best trick in the math book. The first best trick in the math book is multiplying cleverly by 1. The second best trick in the math book is adding 0. So if I added 2 squared to balance it out, I also need to subtract 2 squared. Okay, beautiful. Okay, so now what's great is this is going to factor into a perfect square. This will factor to an x plus 2 quantity squared. What do we have here? A minus 1 minus 2 squared, 4. Negative 1 minus 4, I'll get a minus 5. We've done it. We've written it in the vertex form. Now you might be a little bit skeptical. You might be a little bit skeptical. Maybe you see a plus sign here, a minus sign here. You see a minus sign here, you see a plus sign here. That's okay. What I like to do is let's think about this intuitively. What have I done to the graph of x squared? Well, since I've added 2 directly to x, I've actually shifted the graph to the left 2 units. So let's write that. I've shifted x squared to the left by 2 units. And since I'm subtracting 5 from the outside of the function, I'm shifting x squared to I'm shifting x squared down 5 units. So now I know exactly where the vertex is. For the graph x squared, what have I done to it? I've taken the vertex, I've moved it to the left 2 units and down 5 units. So a really rough sketch of this function is quadratic. I've moved it to the left 2 units, -2, and down 5 units. So its vertex is right here. And it'll be a happy face. It'll be a happy face. Okay, this is, again, still just a rough sketch. Okay, my computer just went into rest mode. So again, I've taken the vertex, I've shifted it to the left 2 units, and down 5 units. Down 5 units. So I have a nice, rough sketch of this graph right here. Now we'll do more detail here, I think in the next lecture. Okay, so beautiful. So notice the vertex is at -2. The vertex is at -2 and -5. And if I look over here, remember here we would say that the vertex is at h and k. Well, over here, think about this. Maybe another way to think about this is the same thing as x minus a -2 squared plus a -5. So our h is the -2 and our k is the -5, which is exactly the vertex. Okay, let's do another example. Okay, so let's do an example. Let's say f of x is equal to, let's say, 5x squared plus 30x plus 4. So what I want to do here is I want to write this in vertex form so I can see how it's a transformation of x squared. So what we want to do is we want to go ahead and complete the square on the first 2 terms here. But notice here, I don't have something of the form x squared plus bx. The coefficient in front of x squared is not 1, it's a 5. So the first thing I'm going to do when I group the first 2 terms together is I'm going to go ahead and factor out a 5. So if I factor out the 5, I'll be left with 5. And I'm going to also leave myself with a little bit of room here. So if I factor out the 5, I'll be left with x squared plus 6x plus the 4. If I distribute the 5 back in, 5 times x squared, I get 5x squared. 5 times 6, I get 30. Beautiful. So now we'll go ahead and complete the square on the x squared plus 6x. Now our b is the 6. So what do? We're going to take that 6, we're going to cut it in half, and we're going to square it. So I have a 3 squared that I'm going to add inside these parentheses. So if I add a 3 squared inside the parentheses, this is a very common mistake I see a lot of students make here. The common mistake would be, since I added 3 squared, they would subtract 3 squared here, but be careful. I didn't just add 3 squared, I actually added a 5 times 3 squared because of this 5 on the outside of the parentheses. This 5 distributes back in. Really what I added was a 5 times 3 squared. So I need to subtract a 5 times a 3 squared. So I balanced everything out. Okay, so f of x, this will be equal to, I'll get a 5 times, this will factor to now an x plus 3 quantity squared. Let's see, what do we have right here? This is a 4 minus, what is this? This is a 5 times 9. 5 times 9 is what, 45? So we'll get, what, a minus 41. And there we have it, in vertex form. Notice that this is telling me that I've shifted x squared to the, this looks like I've shifted it to the left 3 units and down 41 units. So right from here I can see that the vertex is at -3 and -41. And in this case, since it's 5 up front, this will be a happy face parabola, and this is where its vertex will be. So here we're getting a lot of practice, or what I'd like us to do is really just practice making sure we can get a quadratic into this form. Okay, let's do another example. Make something a little bit messier. Okay. So for our last example, let's say we have something like, how about -2x squared? How about plus 10x? How about plus 5? So I want to write this in vertex form and find its vertex. Okay? So what we're going to do is we're going to group those first 2 terms together. And since the coefficient in front of x squared is not a 1, we're going to factor out that -2. So f of x will be equal to, I'll factor out that -2. If I factor out a -2, I'm going to be left with x squared, looks like minus 5x. I need to leave myself a little bit of room here. Plus the 5. Okay, so notice if I distribute back in the -2, I get -2x squared. The -2 and the -5 give me back the +10. Okay, so now what we're going to do is just go ahead and complete the square. So again, remember what I do is I grab the middle, I grab the coefficient in front of x, so that's -5. So I will grab that -5. So I'll have this -5. I'm going to cut that in half, and I'm going to square it. I can't reduce this fraction, but this is what I need to add. So what I'm going to do is I'm going to go ahead and add a -5 squared inside the parentheses. But I didn't just add a -5/2 squared. What I actually added was a -2 times a -5 squared. So that's what I need to subtract. So there'll be a lot of negatives here, but what I need to do is now I need to subtract. I need to subtract a -2, a -2 times a -5/2 quantity squared. Okay, let's clean this up. So now I'll have f of x is going to be equal to, I'll get a -2. Okay, how's this going to factor? I like it in this form because this reminds me it's going to factor to an x. This is going to factor to an x minus a 5 squared. Let's do a little aside here and clean this up here. So what do I have? I had that 5. So I'm subtracting a negative, which makes that a positive. So I'll have 5 plus a 2 times a 5 squared, or I'll get a 5 plus a 2. Well, when I square 5 I'm going to get a 25/4. So let's see. So the 4 is 2 2's. One of the 2's in the 4 will cancel with this 2, so I'll be left with a 5. A 5 plus a 25/2. So now what am I going to do? I'm going to do the first best trick in the math book. I'm going to multiply 5 cleverly by 1 by a 2/2. So what I have here, bringing this up over here, I have a 10/2 plus 25/2. I get a 35/2. So that's what I have here. When I clean this piece up, I'm adding a 35/2. Okay. So now we have it in vertex form. This is saying that I'm shifting the graph to the right 5/2 units. I'm sorry, this is saying I'm shifting the graph, to the right 5/2 units, so its vertex will be at 5/2. and 35 halves. And since this a term is negative, this is going to be a frowny face parabola. So there's our lecture on writing quadratics in vertex form. So what's beautiful about this lecture is what we have learned is that any quadratic, anything of the form ax squared plus bx plus c, we can massage it to see it as a transformation of x squared. Beautiful. Thanks for watching. We'll see you in the next video. Take care.